Okay, so in this video I'm going to talk you through question 3 on the Unit 6 end of topic. Just FYI, I've just got back from a quick 2-mile run. I would recommend it for your daily exercise. Get out there while the weather is nice, particularly. It helps. Anyway, so concentrated sulfuric acid reacts with alkenes, alcohols and sodium halides. Name the mechanism for the reaction of concentrated sulfuric acid with an alkene. So, with an alcohol, it's going to dehydrate to give you the alkene, but with an alkene, it's going to give you the alkyl, it produces an alkyl hydrogen sulfate, which, yeah, it's going to ask for the mechanism for in a minute, and that reaction is electrophilic addition. Okay, outline the mechanism for the reaction of concentrated sulfuric acid with propene. So 3 carbons, 1 double bond, to show the formation of the major product. So if you remember, where you have 3 carbons in the chain or more, it's possible to get isomeric products, and one is more likely to form than the other, and that depends on whether it's the primary, secondary or tertiary or tertiary carbocation. I can't see whether that's right. All right. And I suspect that question will be coming up in a minute. So we've got propene. So 1, 2, 3, pop in a double bond. Just check my hydrogens are okay. Yep. Please put the hydrogens in. When I was marking the year 13 mock, quite a few people just missed the hydrogens out. Now I often do that in lesson just because I'm in a hurry, but obviously you need to actually put them in. So then we've got sulfuric acid, which is H2SO4. It's got a sulfur. We've got, where are we? We've got 2 oxygens there in a double bond, and then we've got another 2 oxygens plus 2 hydrogens. So we've got an oxygen bonded to a hydrogen here. So that, that's delta negative, and that's delta positive. And what we've got here, this double bond is an electron dense area, because a bond is ultimately a shared pair of electrons. You've got a double bond, so 4 electrons in total. So that's electron dense. Now remember, we draw our curly arrows from electron source to electron sink, i.e. something where there are electrons, a lone pair or a double bond, towards something with either a positive or, in this case, partially positive charge. Who is that? Hi Molly. I'm just working, darling. You need to go blow your nose. Yeah, go on then. Okay, so we're going to draw the bond, draw the arrow from the double bond to the partially positive hydrogen. I guarantee some people will do it the other way round, and it kind of feels logical to do it from the hydrogen side, because you're adding this to this. It feels like you should draw an arrow going that way, but you must do it from the source of the electrons to something partially positive or positive, because that's what a curly arrow shows, is movement of electrons. So we then need to break this bond, and we're going to push, because the electrons here are repelled by the incoming electrons here. Okay, so the arrow needs to come from the bond onto the oxygen, not from the hydrogen, and not from this bond to here. Hello.
Hi again.
Hi again. So we've therefore broken that bond, and we have where are we? We've attached this hydrogen to this carbon. So that is going to give us HCH, and then this hydrogen, this one here, is now here, and we've broken that double bond, and then we've got C, C, H, H, H. This carbon here, you're right Molly, this carbon here is left with a positive charge. That is your carbocation. And actually what I've done here is wrong. Am I asked for the... No, I'm right. We're asked for the major product. I thought they wanted the minor product. So this is going to be the major product. Okay, we're going to add to this central carbon. We could, because the double bond exists between carbon 1 and carbon 2 here, this could become our positive carbon. We could add the hydrogen there and then this would be positive, and we'd add the group here. That would be the primary. If I just draw in red here to illustrate what I mean, CH3, that would be the primary carbocation. This is the secondary carbocation. This is the major product because it's more stable than this one. And the reason for that is that an increased number of alkyl groups surrounding that carbon have what's called an inductive effect. They're electron releasing, and that stabilises the cation structure. So this is our major product. So what we've produced here, we've lost a hydrogen, so we've got HSO4 minus. Okay, we've lost a proton, which has a positive charge, so we're left here with an overall negative charge. So that gives us SO with a lone pair. Okay, must put the lone pair and a minus charge or negative charge. HO, O and O, and so now we're going to go not from the negative charge, not from the carbon, we're going from the lone pair.
Mommy?
Yes, Molly?
I see.
Can you see Daddy? Good girl. From the lone pair to our positive carbon. Okay, you've got to have the lone pair, you've got to have the charges, or you won't get those marks. And then finally, it does ask you to show the formation of the major product. Mechanism questions don't always actually require the final product if they just want to see the mechanism, but this one does. We are short on space, so I'm just going to say H3C, CH, CH3, and this now has OS, HO, O attached to it. That is an alkyl, that bit, hydrogen, sulfate. Sulfur 8 means oxygen containing. Okay, right. Next question then asks you to draw the structure of the minor product. So the minor product is going to be the product formed as a result of the reaction via the primary carbocation. So that would be CH2, where are we? CH2, OSO3H, CH2CH3. Explain why the product shown in your answer is the major product. I already discussed that for 2 marks. So we need to say something about the fact that major equals the secondary carbocation. And I'm not writing a word perfect answer here, but just getting down the key points. Major is the secondary carbocation, equals more stable. And then the second mark's going to come probably from saying something about why it's more stable. And I'm going to write about the inductive effect of the alkyl groups. Okay, right, question E. Butan 2O reacts with conc sulfuric acid and it forms 3 isomeric alkenes. So we already discussed that briefly. Alcohols react with sulfuric acid to dehydrate and give the alkene. So butan 2O, 1, 2, 3, 4, OH. Okay, so it says 2 of the alkenes are stereoisomers. There are 3 isomers in total. So it could be that we dehydrate, we lose this, and we form a double bond here. Okay, it could be that we dehydrate and we form a double bond here. So we could get but1-ene, or we could get but2-ene. 1-ene, 2-ene. If we get but2-ene, then that is going to give us some EZ isomerism. So Next thing is to note the fact that it asks for the skeletal formula, so we need to make sure that we do that. If you, oh, blooming thing. What's it doing? Sorry. If you find it hard to work in skeletal formulae, then start with the displayed and then convert it. It's a little more time consuming, so you need to kind of weigh up whether it's worth it for the mark. But anyway, so skeletal formula then. First of all, we've got 1, 2, 3, 4. Okay, and then I'm going to put double bond on carbon 1, could be either end, doesn't matter, and the name of that is going to be but1ene. Okay, next up then I could have 1, 2, 3, 4. I'm going to put the double bond on carbon 2, and that would be but2ene. However, this is going to exist in EZ isomers, so we need to figure out which one it is. And so this one here is, we've got our carbon, there'd be a hydrogen here, and there'd be a hydrogen here. So this is our priority group and this is our priority group compared to that, and they are on opposite sides, so that is E, but2ene. And then finally we could have 1, 2, 3, 4, put in the double bond. Again, with skeletal, so we're not showing it, so don't put that in, but hydrogen's on the same side, priority groups on the same side, so that is Z, but2ene. Okay, next question. A byproduct of the reaction with butan-2-ol with concentrated sulfuric acid has that molecular formula. Okay. Name this byproduct, identify the role of the sulfuric acid, and suggest the name of the method that could be used to separate the products. So C4H8O, if we have an alcohol and sulfuric acid can act as an oxidizing agent, so it's going to oxidize the alcohol, and we can see from the molecular formula we've still only got one oxygen, so it's not going to be the carboxylic acid, because obviously the functional group for that would be that, so we'd have 2 oxygens, which means it must have just partially oxidized it to an aldehyde. So the byproduct name is going to, oh goodness, sorry, no, I'm wrong. It's going to be a ketone, because butan-2-ol, read the question, Mrs. Horton, is a secondary alcohol. So we're going to get a ketone, okay? So we're going to get butanone as our byproduct. And I mean, you could say but2-one or butan-2-one, sorry, but it doesn't really matter because it can only go on carbon 2, whichever way you've come at it from. The role of the sulfuric acid, we already said, is an oxidizing agent. And separation method, to separate these, you would use distillation. I guess you might say fractional distillation. Yeah, okay, that's question 3.